Hey everyone, welcome back to The Explainer. So, have you ever stood under a massive steel bridge, or maybe looked way up at a towering skyscraper, and just wondered how on earth millions of pounds of steel and concrete just sit there? It honestly feels a bit like magic, but it's actually a really beautiful, rigorous branch of physics. Today, we are exploring the concept of static equilibrium, or as it's known in our source material, Etizanes Sacconi. It's essentially the hidden mathematics that literally holds our built environment together, completely preventing everything around us from collapsing or just spinning out of control.
Okay, taking a quick look at our agenda for today, we're going to cover the concept of static equilibrium, the basic conditions of equilibrium, statically determinate structures, how we analyze trusses, and finally we'll wrap up with redundancy and mechanisms.
All right, let's dive right into this fascinating concept. So today's explainer is actually pulled straight from the Sudanese Engineering Sciences curriculum textbook, specifically their third-year secondary physics and engineering materials. And honestly, what I really love about this source is how it takes the super abstract, sometimes intimidating physics of how things stand still and makes it just incredibly intuitive. It basically breaks down the raw forces of nature into a universal mathematical language that we can easily read and calculate. Starting off with Section 1, the concept of static equilibrium. Before we can even think about building a skyscraper, we have to answer the absolute simplest question. What makes an object sit perfectly still amidst all the chaotic forces of the world? I mean, gravity's always pulling down, the wind is pushing sideways, the ground's pushing back up. To answer that, we have to look at resultant forces. See, an object in static equilibrium doesn't just sit there passively. It is actively canceling out every single force trying to move it. The textbook defines it really clearly. The object is stationary because the resultant, so the net sum of all forces and moments acting upon it, equals absolute zero. It is literally a perfect invisible tug-of-war where absolutely nobody is winning.
Moving right along to Section 2, the basic conditions of equilibrium.
So, to actually guarantee that stillness, engineers rely on these three golden equations. It's a beautiful rule of threes, actually. First, all horizontal forces, the pushes left and right, they absolutely must cancel out. Second, all vertical forces, gravity pulling down and the earth pushing up, those must cancel out too. And third, the sum of all rotational moments has to be zero. Think about it. If you push on a seesaw, it spins. Structures can't spin. Any twisting or turning forces must be entirely neutralized by a counter twist.
Okay, so we have our rule of threes. Left equals right, up equals down, clockwise equals counterclockwise. Pretty straightforward, right? But before we get bogged down in the heavy math of actual buildings, let's take a quick breath and ask ourselves, how do these three simple bullet points translate to a massive, complex structure in the real world, like a huge sports stadium roof or a suspension bridge?
That brings us to Section 3, statically determinate structures. Now this right here is the absolute sweet spot for structural engineers. A statically determinate structure is one where those three basic equations we just talked about, horizontal, vertical, and rotational, are literally all we need. If a structure is determinate, we have exactly enough equations to solve for every single unknown support force keeping it standing. It is mathematically elegant, it's totally predictable, and most importantly, it's safe. But beware, because you can't just randomly add supports. You might think to yourself, hey, I'll just add 10 extra concrete pillars. That'll definitely make it safer. But if you just start slapping on extra supports without thinking it through, you create what's called a statically indeterminate structure. You end up introducing so many unknown reaction forces that those three basic equations just aren't enough to solve the puzzle anymore. You've essentially created a structure that completely defies simple math.
All right, let's step it up to Section 4, analyzing truss equilibrium. Okay, so we know what a determinate structure is. Now, welcome to the boss level, trusses. You definitely know them. They are those beautiful interconnected triangular frameworks you see supporting warehouse roofs or making up the sides of railway bridges. The cool thing is we can boil down the physical complexity of these massive, sprawling frameworks into a single, clean equation, using the variables straight from our Arabic source text, where joints or nodes are ta, members or physical rods are dod, and reactions or support forces are ra. The formula dictates that 2 times ta must equal dod plus ra. Literally every single connection point, every steel beam, and every concrete support is accounted for in this one simple balance scale. Let's actually look a bit closer at the R in that equation, the reactions, or basically the support forces keeping the truss anchored safely to the ground. Remember our rule of threes from earlier? Well, 3 is the exact minimum number of reaction forces required for a standard plain truss to be safely anchored and perfectly stable. It all connects right back to those 3 golden rules of horizontal, vertical, and rotational stillness.
Which leads us to our final part, Section 5, redundancy and mechanisms. So, we have the magic equation for a perfectly stable truss. 2 times the joints equals the members plus the reactions. But as naturally inquisitive learners, we have to ask, what happens when we test a real-world design and the 2 sides of that equation just don't match up perfectly? Well, if the equation is perfectly balanced, you're good. You have a safe determinant structure. But if 2 times the joints is greater than the members and reactions, you don't actually have a building anymore. You have a mechanism. You literally have too few beams, and your structure is basically a dangerous moving machine that will definitely collapse under a load. On the flip side, if 2 times the joints is less than the members and reactions, you have too many parts. You have a statically indeterminate structure.
And this is exactly why engineers can't just guess their way through construction. You can't just throw extra steel at a problem and hope for the best. Adding beams willy-nilly doesn't guarantee a safer structure. It creates redundancy. And redundancy means our basic, reliable math completely breaks down. It basically guarantees a massive mathematical headache, requiring super advanced computer modeling just to figure out how all those extra forces are interacting with each other.
So, we've journeyed all the way from the simple definition of standing still to the incredibly precise mathematical balancing act that keeps our massive bridges and roofs from collapsing or turning into moving mechanisms. But knowing that the math of static equilibrium is so incredibly strict, I really want to leave you with this thought to ponder. If simply adding more material makes a structure mathematically redundant and infinitely harder to calculate, is over-engineering a structure actually a blessing, or is it a burden? Just keep that in mind the next time you drive over a truss bridge. Thank you so much for joining me on this explainer, and as always, keep questioning the world around you.